Okay, so it is time to talk about climate change, which it feels like we've been building towards all year long. It is certainly one of the topics that most of us associate with environmental science. And we have certainly been building towards it with our conversations about atmospheric pollutants and about the greenhouse effect. So let's jump right in and take a look at our PowerPoint here. So this is the fifth objective of Unit 9, Global Climate Change. So before we talk about current climate change, let's talk about the history of climate change on our planet. So one of the arguments that many people make about climate change is that, well, the climate has always changed. And that is absolutely true. Earth's climate has varied over geologic time, mostly due to variations in the Earth's orbit around the sun. So it varies in a couple of ways. One of them is what we call eccentricity, and that has to do with the shape of the orbit. And so as the shape of the orbit changes slightly, depending on the other planetary objects acting on the Earth, it comes closer to and farther away from the sun at different times. And this is about 100,000 year cycle. Obviously, the little image that we have here below is exaggerated so that you can see it. The actual change is much, much, much smaller than this. Okay. And then the other way that it changes, you may have heard that the Earth has a wobble. And so it varies in obliquity, which means that the angle of the tilt of the Earth relative to the orbital plane changes a little bit between 22.1 and 24.5 degrees. We usually say that it's 23.5. So it does change a little bit. That one is about a 40,000 or 41,000 year cycle. So it's a long, long cycle. It's not responsible for rapid change. Neither is our changes in eccentricity. So these are predictable variations in the climate. They're called Milankovitch cycles, and you can actually look at data about these over time. So what do we know about our historical climate, and how do we understand and how do we interpret that? So scientists have measured and estimated Earth's historical temperature and carbon dioxide levels using three main pieces of evidence. So the first one is these shells of these ocean organisms called foraminifera, and different species have different ranges of tolerance for heat. And so by looking at what species are present at different times in the ocean's history, we're able to tell what the average ocean temperatures were based on what the range of tolerance for that particular species is. And then another way that we look at this is by taking ice cores or samples of ice in glaciers. And we look at the air bubbles in those ice cores. And we're able to date those ice cores very effectively. And they contain ancient atmospheric gas. And so by measuring the proportions of the gases in those air bubbles, we're able to determine carbon dioxide levels from hundreds of thousands of years ago. And then another way that we're able to use ice to date or to tell us about the climate in the history is by looking at the concentration of oxygen 16, which is our most common oxygen isotope, versus oxygen 18. So much like we use carbon 14 to date previously living things, we can use oxygen 18 to date ice or to date water. And so we know that when we have higher levels of oxygen 18, it indicates that there was a higher temperature. So if we take a look at this graph, you can see these Milankovitch cycles, and you see that spike about every 100,000 years where we are a little bit closer to the sun. And you can also see that it isn't exactly 100,000 years. So you see it cycling up and down, and you see the blue line represents carbon dioxide concentrations in the atmosphere in parts per million, and the red represents temperature. So we can see that as carbon dioxide levels go up and down, so do temperatures. Our global ice ages are usually followed by warmer periods, and they occur about every 100,000 years. And our carbon dioxide levels are strongly correlated with temperature, but the reason for that isn't fully understood. So what are the effects of climate change? Well, when we have rising temperature, we may have habitat loss, which leads to species loss, drought, the desiccation or drying out of soil. We have increased heat waves. We have increased precipitation in some areas because the ability of the atmosphere to hold water changes with temperature. We also are going to talk about rising sea level that's due to polar ice melt and thermal expansion. We're going to talk about the melting of permafrost, which is those permanently frozen tundra soils that as they melt, they thaw, they release methane gas and carbon dioxide from anaerobic decomposition. So these are positive feedback loops. Unfortunately, the effects of climate change, as temperature rises, those soils thaw. That increases both methane and carbon dioxide concentrations in the air, which causes temperature to rise more. So we have that positive feedback loop. These are the risks of global warming if it rises by as little as 2 degrees Celsius, which was the goal of the Paris Climate Accord, was to keep that global temperature change under 2 degrees Celsius. And you can see that the scale we're using is from an undetectable to a very high risk. And this is from no change up to a change of 2 degrees Celsius. And you can see that coral die-off starts to be significant even at a 1 degree Celsius change. So there are some pretty significant impacts that we can see here. Obviously, impacts on tourism, impacts on human beings with morbidity and mortality. So significant changes, even with just 1 to 2 degree Celsius changes. Near and dear to our hearts are the impacts on coastal communities, because we are considered a coastal community. One of the most significant impacts on coastal communities is going to be property loss and damage. If communities are fortunate, they're going to be able to relocate, but poorer ones may not be able to relocate. They may not be able to relocate to build up to protect their coasts. Seawalls, other barriers, riprap can always be built higher, but this just delays the eventual flooding. Barrier islands, which are those islands that shift and change with the tides, tend to buffer our coastal communities and ecosystems from wind and waves. And as sea level rises, those barrier islands may actually be underwater. So of course, you guys are familiar with barrier islands living in this area. The Outer Banks of North Carolina are barrier islands, and then there are also barrier islands off the eastern shore of Virginia. So these barrier islands reduce the impact of waves on the shore, so they help with preserving our coastline. They also help to mitigate the impact of storms as well. And you guys are also familiar with the problem of inundation of those low-lying roads. If you've ever tried to go down to North Carolina after a hurricane, it's very common for North Carolina 12 to be underwater or to be overwashed with sand, and for it to take several days for the communities to be able to reopen the roads. It also causes damage to ships as we have rising sea levels. Okay, atmospheric currents are also impacted. So the Hadley cell, you might remember, as the cell that rises up at the equator and falls near the 30th parallel. And as the global climate change increases, as global warming increases, the temperature difference between the equator and the poles is going to decrease. So that's going to mean that the air that's rising at the equator is actually going to travel farther before it sinks. So instead of sinking at the 30th parallel, it may well sink a little bit higher, closer to 35. And we remember that at the 30th parallel, we have deserts because that is falling dry air. And so this may result in some desertification near higher latitudes above 30 or below 30. It's also going to shift those subtropical zones, and it's going to expand the tropical zones. This also weakens the jet stream. So as the Arctic warms faster than other areas of the Earth, the temperature difference between the equator and the poles weakens. And so the jet stream actually weakens and becomes wobblier, which allows that cold Arctic air, instead of being contained in that strong jet stream with that big difference in pressure between below the jet stream and above the jet stream, it is actually able to push down into areas that the jet stream doesn't normally travel, and our cold air moves south. And so when we hear about these events with the polar vortex, so the major freezes and storms that we just had in Texas a few weeks ago, and all through the American Central Plains, those were because of that destabilized jet stream. This can lead to these extreme cold spells in the eastern US and particularly in the American plains. It also can lead to dry spells in the western US because the moisture is not coming into that area the way that it normally does. There are going to be impacts on marine ecosystems as well. So some new marine habitats may be formed by those rising sea levels. That flooded coastline may now become wetlands or marine ecosystems. But some areas of the ocean are going to become too deep to receive sunlight. And that means that that photic zone, that zone where photosynthesis is possible, is going to shift up. It's going to become further from the ocean floor. So coast is going to change, deep water is going to change, but all throughout the ocean is going to change as well, because that warm water is going to hold less oxygen. So lots of fish populations have declined, or they may migrate to cooler waters. This is affecting our fisheries as well. Okay, it also, not only does it impact ocean temperatures, it impacts ocean circulation. So thermohaline circulation is the circulation, the global ocean currents that are driven by differences in temperature, hence the thermo part, and salinity, which hence the haline part, because those are halogens, right? Chlorine is a halogen. So these global ocean currents that are responsible for redistributing warmth from the equator, but also mixing salt and nutrients by moving ocean waters around, could actually be slowed down or stopped altogether. So these are our prevailing thermohaline circulations, and you'll notice that warm water from the equator moves up through the Atlantic and comes down off the coast of Greenland. It moves down through the Atlantic and out through the Indian Ocean and into the Pacific Ocean, and then back down along the Antarctic and up the coast of South America. So we have these circulations that are driven by differences in salinity and differences in temperature. But as ice melts all around the planet, particularly up near the poles, so the ice melt near Greenland adds a whole lot of cold fresh water that gets built up in the North Atlantic. Now, normally as the water is driven north, it actually dives down. But because this water is less dense than the salt water, it can't sink. And so we don't get that diving down of the cold water current. And so it actually slows this whole Gulf Stream water from moving up. It cools Europe off and it slows the overall global circulation. Another interesting factor of global warming is that it is unequal. So our polar regions are warming faster than other regions, and that's called polar amplification. And a big reason for that is that there is more land in the Arctic than in the Antarctic, and there's less water to absorb the heat. And so you can see that the anomaly, the change in temperature from 1951 to 1980 is much, much more significant over the Arctic than pretty much anywhere else on the planet. So our melting, this causes our sea ice to melt, which exposes ocean water. And of course, because the ocean water has a lower albedo or lower reflectivity, that means it absorbs more of the heat coming from the sun. Snow and ice are going to reflect that heat because they're light surfaces, but the water is a dark surface. It's going to absorb that heat. And as it absorbs that heat, it's going to melt more ice, which is going to expose more water, which is going to absorb more heat, which is going to cause the temperature to rise, which is going to cause more ice to melt. And here we are trapped in this positive feedback loop again. That distribution of tropical heat to the poles from that normal thermohaline circulation also warms the poles. Okay. Whoops. All right. The melting of permafrost we talked about at the very beginning, and we're coming back to. These permanently frozen tundra soils, remember that's the definition of a tundra soil, they begin to thaw as we have increased atmospheric temperatures. And when that happens, it releases both methane and carbon dioxide that has been frozen. So this decomposition of soil begins, or decomposition begins in the soil, and that releases methane and carbon dioxide, which of course causes temperature to rise, which causes more thawing of the soils, so more released greenhouse gases, and here we are trapped in the positive feedback loop again. The air pollution also adds soot and other particulate matter to the atmosphere, which gets distributed to the poles by that atmospheric circulation. And that darker ice also absorbs even more heat due to lower albedo. So we have a whole lot of positive feedback loops here. So here we have a picture of soot-covered ice. Doesn't even look like ice, but that causes it to melt faster. And of course, we have impacts on our polar ecosystems. I know everybody was all excited to talk about the polar bears. When we lose our Arctic sea ice, we lose habitat. Seals use the Arctic sea ice for resting. They come up to holes in the ice for breathing. Algae actually grow on the underside of the ice, and that is the base of the Arctic food web. So without that surface on which the algae can grow, we are losing our primary producers. And of course, polar bears live on Arctic sea ice and rely on those breathing holes in order to hunt seals. So that Arctic sea ice, that's the foundation of our food chain with the algae and the diatoms and the plankton and the copepods and cod and seal and polar bears. So without that habitat, we are in danger of losing an entire food web. And here's our practice FRQ that we'll start with at the beginning of class. So as always, if you have any questions, let me know.